All right, here we are, 9.5, day number 1. It's been so long since my last post. I mean, so many things have happened. Winter break, kids getting sick. Um, got a nice quarter zip. This is just beautiful. It's got a flag on the left shoulder. Just feel so good about that. Freedom is not free, children. But today we're going to talk about math induction. Math induction is an awesome process, and it actually allows us to do many things in calculus. You may not realize it, but later on you will. So let's get started here. This, to start off with, should not be a 3. This should be a 5. Thank you much. Let's get started. Those are the quiz answers, in case you were wondering. Good for you. I'm not doing this toothpick activity right now because I don't care. I want to talk about math induction. So math induction consists of 3 steps. Step 1 and 2 are setup steps, and step 3 is an execution step. I know it sounds kind of like Renaissance-ish, like set up, execute. Okay, but that's what math induction is. We're going to be proving things using letters today. How do you feel about that? Yeah, letters. No, I'm not good at them either. I do with the numbers. I want to jump into, okay, the base step consists of 2 steps, and the induction step is going to be awesome. So let's do some Renaissance. Let's execute this. What happens in step 1? Okay, so we're going to take some series of numbers, and we're going to turn it into an equation so that, for example, if I were to go back a couple slides to the one I just skipped over, but if I went back to this, I could show that 2 plus 4 plus 6 all the way up to however many number of terms I want, I can actually simplify to n times n plus 1. Now, someone might be like, well, I can prove it's true. Watch, I'm going to plug in a 6. And they'd add up 2 plus 4 plus 6 all the way up to 12, right? And then they'd say, yeah, I'm going to plug in a 6, and that means that that would equal 42, and if I added up all these, that equals 42, so it's true. But it's not always true if you just pick some case. So what do? Well, what we do is we set up and we show that it's true for 1, and then we do a weird thing, but in step 2, we assume it's true for some value k, which we don't know. And in step 3, we execute this thing. We execute it not by the guillotine, by showing it's true for k plus 1. So if I know it's true for k, and I prove it's true for k plus 1, that means the next term is always true as well. So that means we can climb ourselves up the old ladder. We show it's true for 1. We assume it's true for k. If we can prove it's true for k plus 1, then isn't the next term it's always going to be true for the next term. So that's the process of induction. If it doesn't make sense yet, it will in a moment. So here's an example, and this is a classic. All right, step 1, what do? I prove it's true for n equals what? 1. Start at 1. Got to take one step, right? You're a little kid. You're like, I don't know how to walk. Apparently you can talk, but you can't walk. And your parents are like, just take your first step, little one. And you fall down. They're like, oh, you're okay. You got to take first step first. So you plug in a 1. So show true for n equals 1. Let's show this is true for n equals 1. Well, how many terms would I have on the left side of that equal sign if n equaled 1? Well, only 1, right? I'd stop right there. So is 1 equal to, and I'm going to plug a 1 in for n on the right side as well, is 1 equal to 1 times 1 plus 1 over 2? Well, that'd be the same as 1 times 2 over 2. Is that true? Yeah, it's true. Okay, so that's not groundbreaking. That's the easy step. Step 2 is also easy because you don't have to do anything other than assume it's true for k. Oh my gosh, what does that even mean? All right, so let's assume it's true for k. Well, in step 2, if I assume it's true for k, for n equals k, that means 1 plus 2 plus 3 plus all the way up to k would equal, now I'm plugging a k in for n. So that means it'd be k times k plus 1 over 2. Step 2 is done. You didn't have to prove anything. You're just assuming that's true. Because now we're going to get to the execution step, and we're going to prove it's true for k plus 1, which means then we will have proved it's true for all numbers greater than or equal to 1. Let me pause the video right now. I see some Bambis out there. All right, so step 3. Step 3 is prove true. I feel like I should put like a battle axe here or something. Oh, that was bad. Execution step. Prove true for n equals k plus 1. Okay, so we're about to get some ugly algebraizing going on here. It's about to get ugly. Yeehaw. Who did that? Little Texans out there. 1 plus 2 plus 3 plus all the way up to k. I'm going to include that last statement that we did in step 2. And then I'm going to add a k plus 1. And notice I put it in parentheses so I don't get confused. We're going to show that that thing is equal to, now let's recall what we had. We had n times n plus 1 over 2. What are we plugging in for n in this case? Not k. K plus 1. We're proving it's true for n equals k plus 1. So that means I have a k plus 1 times a k plus 1 plus 1. Okay, let's just highlight some things so we know where we're at here. I think blue and yellow go okay together. K plus 1 went in for n. K plus 1 went in for n. With me? All right. So let's continue. I get asked this question a lot. Mr. Ludd, why don't you skip from step 1 to step 3? Normally not in that type of language, but because guess where step 2 shows up? Oh, looky there. So what can I replace 1 plus 2 plus 3 all the way up to plus k with? That thing. K times k plus 1 over 2. So I'm going to do that. I'm going to do a direct replacement. K times k plus 1 divided by 2. I'm going to add what I have here, which is k plus 1. And I want to show it equals this thing over here. Now, the thing about math induction is you can't work both sides of the equation at the same time. This is a proof, folks. You can't manipulate both at the same time. You can only work on one or the other. I always work on the left side, make it look like the right. So what would I do in order to combine these two terms? To combine this term and this term, what should I do? Get a common what? Denominator. Okay, so if I want a common denominator, I want both to be divided by 2, so I got to multiply top and bottom of that second term by 2. All right, let's see what happens. Ooh, I got something cool. What do both of those contain? K plus 1. Let's take a k plus 1 out and let's see what happens. Actually, I'm going to do this too. I'm going to pull out a 1/2 because they both contain a 2 in the denominator, right? They both contain a k plus 1. So if I were to pull out a k plus 1 out of both of these, what's left? K plus 2. Whoa, we're almost there. We're almost there. I got a 1/2 k plus 1. And I want to make a k plus 2 look like this. Could I make k plus 2 look like that? Heck yes, I can. I can split it. This would be k plus 1. This would be k plus 1 plus 1. And 1/2 distributed about that would be said thing. I can place parentheses right here. And look what I did. By induction, I've shown that's true forever. So I've proved it. Therefore, since P of n, now I'll tell you what that is in a second, is true for n equals 1, n equals k, and n equals k plus 1. Remove this. Then P of n is true for all n greater than or equal to 1 by math induction. And most mathematicians put their own little signature on their proof. And this is my signature, has been since college. That's my signature. And I can't tell you why. I can't. Well, okay. I've had students prior to ask me, do I really need to show it's true for n equals 1? Okay. Step 1 in this case, as we know, is show true for n equals 1. Okay. Just as a formality, I'll do it. 1 squared. Okay. Is 1 squared equal to, and I'm going to plug a 1 in everywhere, 1 times 1 plus 1 times 2 times 1 plus 1 over 6. Let's see if it's true. That'd be 1. This would be 1 times 2 times 3 over 6. Is 1 equal to 6 over 6? Yeah. Okay, step 1, done. All right, step 2 is the easy step, right? That's probably the step where in the Renaissance days they were like, hey, you want a free gift, come through this door. Why don't you put your head on this piece of wood? Right? And then step 3, they're like, thanks for playing. Maybe that's how you feel. Step 2. I am recording. Okay, whatever. I don't know. Yeah, okay. Step 2 is assume true for n equals k. All right, so we plug it in. We got 1 squared plus 2 squared plus 3 squared plus all the way up to k squared, and we set that equal to, we plug a k in everywhere that you see an n. So that's k squared. What was it? And then k squared plus 1. Is that right? And then 2 times k squared plus 1 over 6. Does that look like the other one except k squareds instead of n's? Oh, yeah, what the heck am I doing? Oh, it's because of this. That fooled me. Yeah, I got sniped on that one. Okay, so those should be k's. All right. Are we all good now? I less confused you? Okay, so step 2 is now done. And so step 3, we're going to prove this ugly thing. And this thing is ugly. We're going to prove true for n equals k plus 1. All right, so everywhere you see a k, or excuse me, everywhere we saw an n, we're going to plug an n, k plus 1. So 1 squared plus 2 squared plus 3 squared up to, I'm going to go k squared and then k plus 1 squared. That rounds out the left side of the equation. On the right side, this is about to get gross. So it was n times n plus 1 times 2n plus 1 over 6. We're going to plug in a k plus 1 for n. K plus 1, that'll be k plus 1 plus 1. That'll be 2 times the quantity k plus 1 plus 1 over 6. Ew. Let's pause for a moment. Okay, so let's highlight what we know from step 2, which is this. And I'm going to replace that, since I see it here, with this thing. And that's not pretty, is it? Is that pretty? No, it's very not pretty. But I'm going to replace that down here. So that is k times k plus 1 times 2k plus 1 over 6. Nothing has changed with my next term, which is that k plus 1 squared term. But I'm going to anticipate that I want a common denominator, so I'm going to multiply top and bottom times 6. This process does seem to show some tendencies to having the same routine, if you will, most of the time. Sometimes it's unique, but most of the time you're going to have to do something like this. Okay, so here's where a little bit of experience is helpful. But what did we do in the last problem? We took a common factor out, right? Do you see a common factor in this one? Well, it's divided by 6, right? Well, what else in the numerator? I see a k plus 1 once in the first term, and then I see it twice in the second term, right? I see a k plus 1 squared right there. So I'm going to take a k plus 1 out. And you guys, there's no coincidence that I see a k plus 1 by itself out here. It's not coincidental. All right, so if I take a k plus 1 out of this first term right here, what's left? K times 2k plus 1, and then we're going to leave the whole thing over 6 down here, right? So k times 2k plus 1. So this went away. I'm going to expand that and write 2k squared plus k. Everybody okay with that? Okay. And in the second one, all right, so that's kind of like, hey, that was the expression that I was left with. In the second term, what am I left with? Yeah, I have 6, and then because I took one of those k plus 1s out, that's gone. So I have 6k plus 6, right? And that's what I have left over. Now I'm going to make that thing right there. I'm going to make that thing, which I'm going to combine like terms, which isn't always a good idea, but in this case it is. I'm going to make that look like this. That's the goal. Because right now I have a k plus 1 over 6, which is cool. That's great. I like it. I have that here, and I have that here. I'm just going to turn that thing into that, and then we'll be done. So how would I do that? Well, let's do a little cleaning up here. I got k plus 1. What would this be? 2k squared. I'd have 7k's, and then a constant of 6 at the end. Could I factor that? I sure as heck hope so. Let's see. That means I have to have a k and a 2k. What numbers would make that work? How about a 2 and a 3? Which one's the 2? 2 with the 2k? Okay, let's see. All right, so that would be 2k squared. That would be plus 2k. That would be plus 6k. That's not going to work. That's going to be 8k. It won't work for us. So let's flip them around. Okay, that would be 2k squared. That would be 3k and 4k, which is 7k and 6. So that'll work. So let's write it just like that. All over 6. Oh, and look at this. K plus 2 is the same as k plus 1 plus 1. 2k plus 3 is the same. Now watch, this is experience talking a little bit. 2k plus 2 plus 1. Oh, what happened there? And that's all over 6. Now, it's not exactly what I want. That last term there needs to change a little bit. I'm going to write k plus 1 plus 1, but then I'm going to take this, I'm going to factor out a 2. If I factor a 2 out of both of those, I get, well, let's take a mental snapshot. Ready? Okay, quit doing that noise. Talia said stop. Therefore, no. Well, you do, but you can write a shortened version. Since P of n true for, I'll break it down to the bare minimum. N equals 1 and n equals k plus 1. Then P of n true for n greater than or equal to 1 by math induction. I think I shortened that a little bit. Ta-da! Verified. Like, subscribe, comment below. Don't be afraid, you know, if you're bored, to just maybe get in the front leaning rest position and do 20 push-ups. It won't hurt you.